Partial differentiation equation is an equation which contains one or more partial derivatives of an unknown function that depends on at least two dependent variables. Usually one of these deals with time t and the remaining with spatial variables. PDE are very important in dynamics, elasticity, heat transfer, electromagnetic theory, and quantum mechanics. PDE has much wider range of application than ODE, which can model only the simplest physical systems. From this question, the given differential equation, which is du over dt equal to k d square u over dx square, and the given condition, which are u x0 equal fx, u negative lt equal u lt, du over dx negative lt equal to du over dx lt. First of all, we let uxt equal to vx gt, where the u in the differential equation given is substituted with vx gt. Secondly, the derivative operator must compatible to each other, where vx is differentiated with respect to x and gt is differentiated with respect to t. Thus, the rearrangement of the equation are made, where the left-hand side equation will be 1 over k gt d over dt gt equal to the right-hand side equation, which is 1 over vx d square over dx square vx. Moreover, we introduce separation constant, which is equal to negative lambda. With the separation constant being introduced, we are able to separate left-hand side equation and right-hand side equation into two equations. Then we rearrange both the equation and make the equation equal to 0. For example, d over dt gt plus lambda k gt equal to 0, and d square over dx square vx plus lambda vx equal to 0. Then we rearrange both the equation and make the equation equal to 0. For example, d over dt gt plus lambda k gt equal to 0, and d square over dx square vx plus lambda vx equal to 0. To avoid trivial solution, we choose vx equal to 0 and v negative l equal to 0 or vl equal to 0. After that, we take d over dt gt plus lambda k gt equal to 0, and we rearrange them into d over dt gt equal to negative lambda k gt, and then we integrate them, and we will get the answer ln gt equal to negative lambda kt plus c. To eliminate ln, we multiply exponential in the equation, and we will get gt equal to e negative lambda kt plus c. After that, we separate both the exponential into two exponential, where exponential negative lambda kt multiply with exponential power of c. Lastly, the answer will be c exponential power of negative lambda kt.
For the case of lambda smaller than 0, the general solution is Vx equal to c1 cos square root negative lambda x plus c2 sin square root negative lambda x. By applying the first boundary condition, we get c1 cos negative l square root negative lambda plus c2 sin negative l square root negative lambda equal to c1 cos l square root negative lambda plus c2 sin l square root negative lambda. Since cos is even and sin is odd, we have negative c2 sin negative l square root negative lambda equal to c2 sin l square root negative lambda, and 2c2 sin l square root negative lambda equal to 0. Now we assume that lambda is smaller than 0, and so l square root negative lambda is not equal to 0. This tells us that sin l square root negative lambda is not equal to 0. We therefore must have c2 equal to 0. Now we apply the second boundary condition to get square root negative lambda c1 sin negative L square root negative lambda equal to square root negative lambda c1 sin L square root of negative lambda and 2 square root negative lambda c1 sin L square root negative lambda equal to 0. From here we will get c1 equal to 0 because lambda is smaller than 0 and not equal to 0. From here, we have two sets of lambda and bx. The first set is lambda equal to n pi over L square and bx equal to cos n pi x over L, where n equal to 0, 1, 2, 3, and so on. The second set is lambda n equal to n pi over L square and bx equal to sin n pi x over L, where n equal to 1, 2, 3, and so on. Okay, now we have two sets of possible product solutions that will satisfy the partial differential equation and the boundary solution. They are u n xt equal to a n cos n pi x over L e negative k n pi over L squared t, where n equal to 0, 1, 2, 3, and so on. The second one is u n xt equal to bn sin n pi x over L e negative k n pi over L squared t, where n equal to 1, 2, 3, and so on. Then we add up the both possible product solution and we will get u xt equal to summation of n equal to 0 to infinity a n cos n pi x over L e negative k n pi over L squared t plus the summation from n equal to 1 to infinity bn sin n pi x over L e negative k n pi over L squared t. Then the coefficient of the cos is a naught equal to 1 over 2L integration of fx dx from negative L to L, and an equal to 1 over L integration of fx cos n pi x over L dx from negative L to L, where n equal to 1, 2, 3, and so on, and bn equal to 1 over L integration of fx sin n pi x over L dx from negative L to L, where n equal to 1, 2, 3, and so on.
For the case 2, lambda equals 0, Vx equals C1 plus C2x, V negative L equals C1 minus C2L, Vl equals C1 plus C2L, V negative L equals Vl, C1 minus C2L equals C1 plus C2L, 2C2L equals 0, C2 equals 0, Vx equals C1 plus 0 times x, Vx equals C1.
For the case 3, lambda more than 0, Vx equal to C1 cos square root negative lambda x plus C2 sin square root negative lambda x. V negative L equals to C1 cos negative L square root negative lambda plus C2 sin negative L square root negative lambda. VL equals to C1 cos L square root negative lambda plus C2 sin L square root negative lambda. V negative L equals to V2. C1 cos negative L square root negative lambda plus C2 sin negative L square root negative lambda equals to C1 cos L square root negative lambda plus C2 sin L square root negative lambda. Negative C2 sin L square root negative lambda equals to C2 sin L square root negative lambda. 2C2 sin L square root negative lambda equals to 0. Since L square root negative lambda not equal to 0, therefore C2 equal to 0. dv negative lambda over dl equals to negative lambda C1 sin negative L square root negative lambda plus square root negative lambda C2 cos negative L square root negative lambda. dvl over dl equals to square root negative lambda C1 sin L square root negative lambda plus square root negative lambda C2 cos L square root negative lambda. dv negative L over dt equals to dvl over dt. Square root negative lambda C1 sin negative L square root negative lambda plus square root negative lambda C2 cos negative L square root negative lambda equals to square root negative lambda C1 sin L square root negative lambda plus square root negative C2 cos L square root negative lambda. square root negative lambda c1 since negative L square root negative lambda equals to square root negative lambda c1 since L square root negative lambda. Negative square root negative lambda c1 since L square root negative lambda equals to square root negative lambda c1 since L square root negative lambda. 2 square root negative lambda c1 since L square root negative lambda equals to 0. So c1 equals to 0.
un xt equal an cos n by x over L e power of negative k n by over L square t. N equal 0, 1, 2, 3. Un xt equal bn sine n by x over L e power of negative k n by over L square t. N equal 1, 2, 3. U xt equal sum from n equal 1 up to infinity an cos n by x over L e power of negative k n by over L square t plus sum from n equal 1 up to infinity bn sine n by x over L e power of negative k n by over L square t. A naught equal 1 over 2L integrate from negative L to L fx dx. An equal 1 over L integrate negative L to L fx cos n by x over L dx. N equal 1, 2, 3. Bn equal 1 over L integrate negative L to L fx sine n by x over L dx. N equal 1, 2, 3. Ux0 equal fx equal sum from n equal 0 to infinity an cos n by x over L plus sum from n equal 1 up to infinity bn sine n by x over L.